In this video, we're going to look at the classification of matter in a very brief overview, and we'll spend some time considering solutions, colloids, and suspensions. Now, matter is defined as anything that has mass and occupies space. And there are two types of matter. We have pure substances and mixtures. Let's deal with pure substances first. Pure substances are of two varieties. We have elements of any of the 118 elements on the periodic table would be included here. And we have compounds, which are chemical combinations of those elements. And it's observed that all of these pure substances, be they elements or compounds, in fact have constant composition and properties, and they cannot be separated into simpler substances by any physical methods such as, say, filtration or boiling or extraction or dissolving. Let's look at mixtures. Mixtures by definition are made of two or more pure substances, and in fact they can be separated by physical means. And mixtures themselves are further subdivided into two types. We have heterogeneous mixtures and homogeneous mixtures. Now, heterogeneous mixtures, by definition, are heterogeneous. That is, they have non-uniform composition. An example would be stones in water. Another example might be a pizza, non-uniform composition. By comparison, a homogeneous mixture is one of constant or uniform composition. I want to spend our time looking at the different forms of homogeneous mixtures. And there are three kinds. They include solutions and colloids and suspensions. And we'll deal with each of these in some detail, but by way of introduction, let me just say here that a solution, an example of a solution might include seawater or air or dental amalgams. An example of a colloid includes such things as milk or smog or clouds. And examples of suspensions would include, say, muddy water and even a dust storm. The first type of homogeneous mixture we're going to look at is that of a solution, and there are in fact 7 types of solutions. The first type we want to consider is a gas in gas solution, and air is a good example. It's 78% nitrogen, 21% oxygen, and 1% argon. And within any sample of gas, the distribution of nitrogen and oxygen and argon is completely uniform, which is a characteristic of a homogeneous mixture. There are gas in liquid solutions, such as a carbonated beverage, in which carbon dioxide gas is dissolved in a sweetened aqueous solution. And of course, air dissolved in lake water, seawater, river water is another example of a gas in liquid solution. There are in fact gas in solid solutions. So auto-exhaust gases such as carbon monoxide and NOx and hydrocarbons combine with oxygen, and all of these gases are dissolved or adsorbed on the surface of the catalysts in a catalytic converter, namely rhodium, platinum, palladium, to convert them to less harmful substances such as carbon dioxide, water, and nitrogen. This is an example of a gas in solid solution. We have liquid in liquid solutions. A common example would be vinegar. Vinegar is a 5% solution of liquid acetic acid in liquid water. And of course, another familiar example includes alcoholic beverages, a mixture of ethanol liquid in liquid water. There are solid in liquid solutions, many of them. One example is intravenous solution, which is 0.9% solid sodium chloride, 5% solid glucose in liquid water. Some of my friends jokingly say that when they drink Powerade or Gatorade, they're taking their intravenous fluids. There are, in fact, solid in solid solutions, such as gold jewelry. Now, pure gold is too soft to be used directly as jewelry, but when alloyed with silver and copper together, we get 14 karat gold, and it's still quite suitable as a jewelry material, but a little more durable, that is harder. That's a solid in solid solution. Many alloy steels contain iron as the main component, combined with, say, some manganese for hardness, or nickel and cobalt to make stainless steels. Again, solid in solid solutions. And finally, we have liquid in solid solutions. An example is liquid mercury combined with copper and silver and tin together to make dental amalgams. That is a liquid in solid solution. So homogeneous mixtures include solutions, colloids, and suspensions. And the distinguishing feature between these three types of homogeneous mixtures is their size range. So by definition, a solution is a homogeneous mixture whose particles are smaller than 1 nanometer, which is 10 to the minus 9 meters. That's 1 billionth of a meter. Colloids are homogeneous mixtures with particle size ranging between 1 nanometer and 1 micron, or 10 to the minus 6 meters. That's 1 millionth of a meter. And suspensions have particle size ranges between 1 and 10 microns. And these different particle size ranges give rise to different physical properties. For example, solutions will not separate on standing. They are indefinitely stable. We spoke earlier of seawater. So the dissolved salts in seawater, calcium bicarbonate, sodium chloride, potassium sulfate, they remain uniform and unchanged. If I took a bottle of seawater and sealed it up with no air, let it stand, I could leave it for a decade or perhaps a century, assuming no reaction with the glass container, the composition would remain uniform. It would not change on standing. Colloids, on the other hand, will separate slowly on standing. An example is milk. Now, some literature will say they are stable on standing, and it's all a question of time frame. So colloids with size ranges around the 1 nanometer mark may be stable up to 60 years, and I'm taking this from wastewater analysis. Wastewater purification examples of silt in water may take 60 years to settle if the particles are in the 1 nanometer size, up to about, say, 2 days to settle in the 1 micron size. Suspensions, on the other hand, will separate on standing, some slowly, some relatively quickly, depending on the size within the mixture. And this particular sample is water in which I've ground up some clay very finely and dispersed it in the water. And this took approximately 2 days for this to clarify, for the particulate to settle, and therefore the particulate must have been in a small suspension size range. Another property that derives from this is filterability. Solutions are not filterable. The smallest commercially available filters are approximately 25 nanometers in size, and no filter known will separate solutions. The ions in solutions are extremely small. They're in the picometer range, much smaller than the nanometer range of colloids. Colloids, on the other hand, at least those above 25 nanometers and up, are separable by very, very fine filters or semi-permeable membranes, as we would have in the cell walls of all living creatures, plants, and animals. And of course, suspensions with larger particle size are readily filterable. Now, another interesting property that derives from their size is the interaction with visible light. Now, visible light ranges in wavelength. At the short end, violet is about 400 nanometers, up to the long end, which is about 750 nanometers for red. Take a look at the diagram below here. Now, I'm going to use the analogy of water waves, which I realize is not the same as electromagnetic waves, but since we've all seen water waves, we can visualize this, and it works. Let's envision a series of waves moving towards the shore. When there's an object with larger dimension than the wavelength between the waves, that object breaks the waves and casts a shadow. That is, if I was thinking of this as visible light, the light waves, which are smaller in wavelength than the object, a shadow is cast. We can see this object. Anytime we have an object larger than the wavelength of light, we'll actually see the object. On the other hand, if we had an object which is smaller than the wavelength, it's invisible. So let's consider again waves moving towards shore. Think of yourself standing in the waves. The wave breaks. If you look towards shore, you notice that the wave reforms. In a sense, you're actually invisible. And so it is true with electromagnetic radiation that any object, any particle which is smaller than, equivalent to, or smaller than the wavelength of light, casts no shadow. It's invisible. And so the molecules of oxygen and nitrogen and the atoms of argon in the air are smaller than the wavelength of light, and light simply bends around it, and these molecules and atoms are invisible to us. And so we find that solutions are in fact transparent. We can see clearly through them. On the other hand, colloids, at least those in the size range of visible light, 400 nanometers up to 750 and above, well, they will interfere with light, and they are in fact translucent, not transparent. And I'll explain what I mean by translucent in just a moment. Suspensions, on the other hand, since they have particles considerably larger than the wavelength of light, they will block the light, scatter the light, and they are murky to opaque in appearance. So in this diagram, notice I'm trying to represent here a clear solution which is transparent. So these words are clearly visible through the solution. Here's an example of copper 2 sulfate solution. The ions of copper and sulfate are much smaller than the wavelength of light, and so light passes through, and this would be described as being transparent, or in chemistry lingo we could say this is clear. Now I know in common parlance clear is often used to mean not colored, but in fact the correct use of the word in chemistry is that clear simply means transparent. This is a clear, colored solution. It's transparent because it's a solution. Translucent, on the other hand, means that light will pass through, but any image behind it is fogged or somewhat distorted or blurred, as in the case of this homogeneous mixture. It is a colloid. And here I have a mixture of lead 2 iodide, which is a suspension, as evidenced by the fact that particles are settling rather quickly. Those large particles will be murky and opaque, and light will not pass through it. This room divider is in fact translucent, so the image of this lady behind it is blurred or clouded or fogged. This polypropylene drinking glass is in fact translucent, so light will pass through it, but any object behind it, its image will be blurred. Whenever colloids are discussed, the term Tyndall effect appears, so let's explain that. In this example, I have a beam of white light being passed through a solution first and then a colloid, and we see the observer from the side, that'd be you or I, cannot see the path of light through the solution, but we can see the path of light through the colloid. So light is scattered by the colloid particles that are similar in size to the visible light. And notice particularly that blue light is scattered, and that is the shorter wavelengths, violet, indigo, and blue. Those wavelengths are approximately the same size as the particulate size, and therefore they are scattered. Whereas the longer wavelengths, yellow, orange, and red, would bend and go right around the particulate and pass through. So the observer from the side sees blue. Hence, the shorter wavelengths are scattered more than the long wavelengths. Here's another example, blue eyes. Now, a blue iris in an eye is due to Tyndall scattering in the turbid layer of the iris. I'm taking this directly from Wikipedia. So those of us with brown and black irises have the same turbid layer in our eye, except they have more melanin in it, and melanin absorbs light. In the absence of melanin, the layer is translucent. Light passing through is randomly and diffusely scattered, and a noticeable portion of the light that enters the turbid layer re-emerges via a scattered path. And again, notice it's the shorter wavelengths, the violet, indigo, and blue, that are scattered by the turbidity in the iris layer, whereas the longer wavelengths, yellow, orange, and red, would pass right through. Here's a couple more examples of the Tyndall effect. The beam of light emanating from the headlight of a car is visible on a foggy day. That's because water droplets in the air on a foggy day are in the colloid size range, and they will scatter light. Underwater, shafts of light are visible when we have a dispersion of particles, for example silt, that's in the colloid size range, and this scatters the light. We've looked at some different types of solutions. We mentioned a couple of types of suspensions. Let's now focus on various kinds of colloids. I'll list them briefly first, and we'll look at specific examples. There are in fact 4 types of colloids. There are foams, in which a gas is dispersed in either a liquid or a solid. Another type of colloid is an emulsion, in which a liquid is dispersed in a liquid or solid. A third type is called a sol, in which a solid is dispersed in a liquid or solid. And the fourth type is different than the previous, called an aerosol, in which a liquid or solid is dispersed in a gas. Well, pictures and examples will help here. First of all, let's look at some foams. We said a foam can be gas dispersed in a liquid or a solid. How about gases in liquids? Well, Reddi-wip is basically whipped cream in a compressed gas container. So we have nitrous oxide gas, laughing gas is the propellant typically used in cream. So it's gas in a liquid. What a great marketing strategy. Nitrous oxide or laughing gas is a pleasant anesthetic, and it has a sweet smell. Combine it with the sweet taste of cream and sugar. Sounds like a great sales device. Another example of a gas in liquid is Gillette Foamy shave cream. Carbon dioxide is the usual propellant in a soap solution. So we have gases in liquids are examples of foams. Also, we can have gases in solids. An example you may not be familiar with is pumice. Pumice is lava rock, and notice it actually floats in water. That's because there's carbon dioxide gas trapped inside the stone in lava. One more familiar example is styrofoam. Gas trapped in polystyrene. This is used as an insulating material, say for coffee cups or thermal insulation on a home. As a final example, consider marshmallows. Here again we have a gas trapped in a solid. It's a foam. The gas in, say, some sugary solid. The second type of colloid is an emulsion. An emulsion is a liquid in a liquid or a solid. Let's look at some liquid in liquid colloids called emulsions. We mentioned earlier that milk is a colloid, and in fact it is a liquid that is fat in another liquid, water. Mayonnaise is a liquid in liquid emulsion, that is oil in vinegar or lemon juice. Margarine is a liquid in a liquid, water in oil. It's an emulsion. And finally, moisturizing cream is oil in water. Two liquids together, an emulsion. Well, how about some liquid in solid emulsions, aka gels? Well, one example is butter. Butter has a liquid, water, in a semi-solid or solid, fat. Ice cream is in fact a liquid in solid emulsion, so we have the cream being the liquid in ice. Jello, Jello gelatin. Here, water, the liquid, is in a solid protein. Likewise, cheese is a liquid in solid emulsion, a gel, water, again, in protein. A third type of colloid is a sol. And a sol is a solid which is dispersed in either a liquid or a solid. Let's consider some cases where a solid is dispersed in a liquid. For example, blood. The blood cells are solid. They are dispersed in the liquid portion of the blood called plasma. Paint contains solid pigment dispersed in oil if it's oil-based, or dispersed in water if it's latex or water-based paint. Ink has solid pigments dispersed in alcohol. Here's a couple more examples. Pepto-Bismol is sodium bismuthate dispersed in liquid water. This is good for diarrhea. And we have milk of magnesia, magnesium hydroxide, dispersed in water, and that's good for constipation. So in either case, we have an appropriate colloid, a sol, to treat either condition. Let's look at some examples of sols, which are solids dispersed in other solids. So mortar mix, not the concrete before the stone is added, but the mortar itself is a fine mixture of calcium oxide and calcium silicates, which bind strongly with water to make concrete. And of course, aggregates are added like stone as well. But the mortar itself is a solid in solid colloid with particles in the size range of 1 nanometer to 1 micron. Likewise, any finely ground clays and silts would be described as being sols. And cranberry glass is one example that's commonly given. So there are gold salts dispersed in glass, two solids dispersed. It gives a translucent appearance, and so some of the particles in this would be in the size range of a colloid. The fourth and final type of colloid is an aerosol. And an aerosol is a liquid or a solid dispersed in a gas. Let's look at some examples of liquids dispersed in a gas. Common example is an air freshener. This is a liquid in a propellant gas. Clouds, low-level clouds, have liquid water droplets dispersed in air. The fact that we can see these clouds indicates that their particle size is such that they are similar to that of wavelength of light and therefore disperse the light. Aerosols that are solids in gas include smoke. So we have ash, solid ash dispersed in air. Smog, again we have solids such as particulate in air. Notice the fogged appearance. And finally we have cirrus clouds. These are high-level clouds above, say, 6,000 meters, and these are actually ice crystals dispersed in air. So let's summarize the four types of colloids as to what is being dispersed, and what is the dispersing medium, and what kind of colloid is it. So first of all, a gas, when it is dispersed in a liquid or a solid, it's called a foam. The next phase of matter after gas would be a liquid. When it is dispersed in a liquid or solid, it is referred to as an emulsion. Third phase of matter, we have solid, dispersed again in a liquid or solid. That is called a sol. Notice the consistency, three phases of matter, all in the same dispersing medium, liquid or solid, liquid or solid, liquid or solid. The fourth type of colloid is different. When a liquid or a solid is dispersed in a gas, that is referred to as an aerosol. I realize there are certain types of colloids that are difficult to classify specifically into one of these four groups. Nevertheless, I hope this was helpful, and thank you for watching.